Thank you. Good afternoon, all. I am Mohammad Asaduzzaman from Kwangwoon University, Department of Electronics. I am a PhD candidate. Today, I am going to start my presentations. It's entitled Metal Nanoparticles and 2D-Siloxene Sheets Incorporated Laser-Ablated Graphene-Based Epidermal Pass for Electrolyte Analysis and Monitoring. Before going to discussion, actually, I'd like to say that electrolyte measurements. So it's all about actually potentiometric detection. So why it motivates me? Just I would like to say that if we see the data of our survey, so 4 to 5 million people are deaths each year due to the electrolyte imbalance related to disease. So we need actually continuous monitoring of sweat electrolyte. So to get the early diagnosis data. And it also relates with the early detection of some kinds of diseases like cystic fibrosis, heart conditions, and dehydration, and etc. Some kinds of diseases. So continuous monitoring means actually wearable biosensor. So these are some example of wearable biosensor, and the market of the wearable biosensor is dramatically increasing day by day. So it's also interesting. So some key features of wearable biosensor, it fascinates me. It's actually non-invasive, and also point of care diagnosis we can handle with the personalized healthcare. Right? And my research attention is all solid contact based potentiometric biosensor. So we know that previously, or the common potentiometric biosensor is ion peeling solution, right? So apart from this, we need all solid contact based biosensor because it reduces the size, and to make it wearable, it's very much essential because because of its reduced size. So the first reported also registered potentiometric biosensor was reported by Catrell in 1971. So it's not new. So it's the old field. But our goal is that due to some disadvantage of first reported sensor, that was like the potential dipped due to a potential generated between the ion selective membrane and the current collector. So we are trying to minimize the potential dip and to incorporate some kinds of nanomaterials, we can achieve the very stable output response. So, and all solid state ion sensor electrode actually has some features. So it's a miniature, as right already I said, and it's required low sample volume, also low cost, and one great point is that no inner filling solutions required. So some key issues or challenges we have in our potentiometric biosensor. So I have listed the main 3 obstacles that we are facing nowadays. So one is generating interfacial potentials. So due to these regions, the potential is not stable. And another is under polarizing condition, the potential is not so much stable. And last but not the least, the water layer formations actually. So these 3 major issues we are facing. So my intention is how to overcome these kinds of problem. And to do this among the research scientists, actually, they are using 2 approaches. That means one is using nanomaterials to form a capacitance layer, that is redox capacitance layers, and another is a double layer capacitance layer. So my research interest to works on the using nanomaterials and the capacitive layer, double layer capacitance formations. So that's why I am using some kind of nanomaterials actually. So I mentioned redox capacitance layers. So in this case, normally there are lots of reported papers who have used PWPSS or pani-based, that means conducting polymers. So there are some several disadvantages using the conducting polymers, like it's a sensitivity to light or some kinds of interference. So that's why our intention is to explore some nanomaterials that are not actually conducting polymers, but other nanomaterials. So The issues I have mentioned, 3 kinds of problems. So if we eliminate these kinds of problems, we need to use some kinds of nanomaterials that are hydrophobic as well as conductive and high surface area, because we want to make a capacitive layer, right, double capacitance. So that's why the materials with high surface area will favor the formations of a double layer capacitance, as well as if it has the hydrophobicity property, it will eliminate the formation of water layer formations. So that's why, considering all the properties, I have considered some kinds of goal like low potential drift and very stable response and flexibility also in my research. So our approach is like that. We have considered siloxene based material actually. So siloxene material is a 2D material which has a good electrical conductivity as well as high surface area. And we have considered another nanoparticles, metallic nanoparticles, gold nanoparticles actually. So why gold nanoparticle? So gold nanoparticles actually, it favors the formations of with a high surface area to make a double layer capacitance. So that's why we have included gold nanoparticles with siloxene. Siloxene is itself is a very conductive and as well as it's a very good surface area. And in parallel, the gold nanoparticles also enhance the surface area. Also, it increases the ion to electron transition. So all 3 conditions actually, considering all the 3 conditions, we have selected 2D-Siloxene and gold nanoparticle based nanocomposite as a solid contact layer in our in this work actually. So already I mentioned it's give us good surface area, electrical conductivity, as well as hydrophobicity. So hydrophobicity comes from the 2D-Siloxene. So it is a well-known hydrophobic material, siloxene. And the flexibility come with actually laser-ablated graphene. So we have taken PI, polyimide film, and just with the cost-effective and facile method of fabricating LAG, just laser scribing the PI film. Also, it acts as a substrate or current collecting layer, right? So this shows the schematic of synthesis of 2D-Siloxene. So calcium salicylate, HCl. So it's etching process 3 days, long time. So it is the calcium part. Then it forms the 2 thin double layers, multi-layer structure of 2D-Siloxene. And this shows the fabrication technique of our epidermal patch. So it's the 2 sensor. One is a reference and 2 working. One working is sodium ion and another is potassium ion sensor. And we have functionalized this and use the ISM, ion selective membrane, using the sodium ionophore as well as the valinomycin for the sodium and potassium IC respectively. It's the physical morphology of 2D-Siloxene material we have synthesized. So it shows a very good laminar structure of 2D-Siloxenes, and the right one, B, shows the electrodeposited gold nanoparticle within the porous structure of the LAG, and the right one segment shows the individual segments of a 2D-Siloxene. So overall, I can say that siloxane nanosheet and porous laser-ablated graphene, which is a porous structure, so it favors the transportations of ion from the electrolyte and the ISM also. And the presence of a gold nanoparticles favor to the ion to electron transition, as well as it gives high surface area. So this combination actually works well. So ion transporter favored by porous structure biology, already mentioned, and interlayer, also the interlayer voids of the 2D-Siloxene. So 2D-Siloxene materials have some kinds of voids, interlayer voids, so which facilitates the ion to electron transactions. And now I would like to go to the material characterization too. So this is the EDS image of our material. So it shows all the desired elements except the calcium, because we have etched the calcium part. So the presence of carbon, silicon, gold nanoparticle, and oxygens that are come from our proposed solid contact material. So we can say that we have done successfully to the material of siloxane synthesization, so trace of elements except calcium and the presence of electrodeposited gold particles. And then we have tested some kinds of hydrophobicity test of our solid contour material, because it is very much essential, actually, to eliminate the water layer formations in between the interface of ISM and the solid contact layer. So our solid contact layer, we have measured the hydrophobicity in terms of water contact angle measurement. So we have got a water contact angle is 116. So it indicates a very good hydrophobic nature of the solid contact material. Then we go for electrochemical characterizations of our ion selective electrode. So this shows the OCP response and the linear heating of our two sensor, sodium and potassium ion sensor. So it shows very good response and very high linear range response for the sodium and potassium ion sensor. And sensitivity we have calculated for the sodium IC, that is around 59.6, and linear range 0.5 to 600 to 36.5 millimole, and LOD is very low and excellent linearity, we can say. And in addition, we have calculated the sensitivity of the potassium IC, that shows 58. It is also very close to an actual response, and linear range is very comparable if I compared with other published paper, and also LOD. And so then we go for another characterizations of our IC. So that is water layer formation test, actually. So suggested by Pires. So this result indicates a very stable response when we change our target analyte to another interfering analyte. And we have calculated the potential drift. So potential drift we have got very excellent value, that is only 3 microvolt per hour. So that indicates its viability for clinical grade. And also we have calculated the potential stability under polarizing conditions. So under polarizing conditions, we have applied ±1 nanoampere current for 60 seconds. So at 60 seconds, when we change, some kind of response we have got, but I think it is comparable compared to other response. And last of all, we have gone through the interference test. In this test, we have included some kinds of biomolecules along with our target electrolytes with others. So the result shows a very good response, selective response for our ion selective electrode. So there is no any significant response to others interference ions or biomolecules. And we have also calculated our logarithmic selectivity coefficient according to bucket at scale, and we have got very good selective nature of our electrode, and we have tabulated all the values. So I can say both the IC shows excellent selectivity. And last of all, we have measured the sweat electrolyte using our sensor. So to do this, we actually collected some sweat from 2 volunteers that are gone through hard exercise, and we collected some sweat, and using actually Becker level test to see the amount or quantifications of the electrolyte. So these are the OCP response we have taken from electrochemical workstations, and using our fitting equations, we have calculated the concentrations of a sodium ion. So from the 2 volunteers, so volunteer 1 is 53.6 millimole, and another is 76.7 millimole of sodium concentrations. And parallelly, we have gone through her potassium IC that gives us 2.2 millimole and 7.8 millimole of concentration. So summary, in conclusions, I would like to say that we have got very good nonlinear response as well as selectivity, and it's a good high stable response. So in future, we are planning to integrate this system with miniaturized system and make it a compact device. So thank you all. Sorry. So I am very thankful. Thanks you all. So I'm very grateful to my lab members and also my research advisor, Professor Yeong. So thank you very much. If you have any questions.